There.
Okay, so it's my pleasure to introduce Brian McGill from the University of Maine to present this latest theoretical ecology seminar. We've got a really good lineup of speakers for actually the next 6 months, really. So do check out our website if you want to see any more of those. But for now, I'll hand over to Brian to give us his presentation. Thank you. And I should say, keep your microphones muted until the end for questions. And after that, we'll open it up to the floor. Thank you.
Okay, thank you. Excited to be here and excited to see I was teaching in the fall, so I couldn't make this seminar, but very excited to be a participant this spring and excited to kick things off. So thanks everybody for coming. I know it's early and late where you are. So let's see if there we go. So I'm going to talk about the idea of community assembly, which I'm going to define as the rules or processes by which it is determined which species will be members of a community, how many species, and what the relative abundances will be. So if you want to take a simplistic view, there's a bunch of species. And I would argue that this is the core challenge of community ecology. Given a list of species and traits and anything you know about species individually, can you predict the vector of abundances of those species in a community? So that's the project I'm taking on. Community ecology really has traditionally had two kinds of approaches. There's sort of a bottom-up approach, which starts with something like the Locke-Volterra equations or the MacArthur-Rosenzweig equations, and starts, which of course deal with 2 species, and then you start piecing together 3 species and 4 species, and you kind of piece it together, and you try and explain a community. But those have certainly hit some roadblocks in terms of parameterization and some other things like that. Also, the sort of non-equilibrial dynamics that seem to occur at community levels. The other big approach is the holism or emergence approach, which is you look at community properties to explain community properties. So the productivity richness discussions, the intermediate disturbance hypothesis, right? Disturbance versus richness. All these kinds of things are really the holism approach, right? It says we don't need to or we can't unpack things down to the level of individual species interactions, but we can take emergent properties of a community like richness, evenness, productivity, and work on that. But there is this third view, and it's very common in many areas of science. It's even common, I would say, in behavioral science and physiological ecology. But the kind of notion that the system that you're looking at is actually primarily being driven by exogenous forces or top-down or external forces. And you see this a bit in community ecology, David Curry's work and lots of other people's work looking at how species richness is controlled by climate, right? Or Rob Whittaker's climate diagram, how the sizes and shapes of species is controlled by climate kind of has this perspective. But I find it curious that there's this nice word for reductionism, there's this nice word for holism or emergence, but I'm not aware of, a nice word in the philosophy of science for this kind of a perspective. But so this is the perspective I'm going to take, and I'm going to see how far we can get in this project of community ecology. And I'll note this has lots and lots of roots. Certainly the work with neutral theory, John Hart's work with Accent, the meta communities, all these things that are looking at the notion of a regional pool, and communities is coming out of a regional pool are starting to adopt this perspective. So I think it's been an ongoing development over the last 10 or 20 years. So, and the one thing I want to note is most of these have an explicit scale assumption, right? So if you're doing holism, and you're looking at species richness and other community level properties, you're either making a claim that it's not worth the trouble or it's impossible to go down to the smaller parts of the system. And conversely, if you're kind of doing the top down, I mean, yes, on some tautological level, the regional pool is the consequence of hundreds or thousands or millions of small local communities added up together. But if you take the top-down approach, you're kind of making the argument that the impact of any one community is so small and meaningless that it doesn't make sense to go in that direction. So there is a scale separation argument for each of these choices. Okay, so the question I want to ask is, how much can we perceive or reproduce community patterns just literally as a mathematical sample? Random sampling. You all probably know the marble model, right? You have an urn of different colored marbles, and different colors of marbles can be different species, and you pull marbles out of that urn, and you see what your local community is. So, neutral theory certainly has a piece of this. Meta community has a piece of this. I think John Hart's work probably comes very close in spirit to this as well, but I literally am just going to use a sampling paradigm. I'm not going to put any local dynamics or anything else on top of things. Just I literally want to see how far you can get with a marble sampling model. And the idea then is that if the regional pool is kind of set up by climate, then we have this sort of directional explanation that flows in the complete opposite direction from what is often the reductionist bottom-up approach, right? Climate sets the regional pool. The regional pool then is sampled randomly to create local communities. You can call this a null model. You can call this a thought experiment. You can call this a random mechanistic model. Some people think those exist. Some people don't think those exist, but this is pretty old territory at this point, that the line between a null model and a random mechanistic model is not necessarily that clear cut. So most of this is summarized in a paper. It was a review paper that I wrote in 2011. But as you'll see, it comes from lots of other people's work, pulling it all together. Okay, so just very quickly, I'm not going to belabor this point, but I do think we have a lot of evidence that the climate does set the basic characteristics of the regional species pool. There's a paper that's work from David Curry looking for different groups, birds, mammals, herps, how potential evaporation affects species richness. And we know temperature and water balance and lots of other things are important. And like I said, Whitaker talked a lot about the size of the organisms. So there's quite a bit of evidence climate structures the basic species pool that's available. I'm not going to belabor that, but that's an interesting starting point. I'm not just pulling the regional pool out of the air. I think we have notions of where the regional species pool comes from. So now I'm going to focus on the right-hand side of this. Literally, and in my mind, I'll just say this to make this concrete, a regional pool is about 100 by 100 kilometers, maybe 200 by 200 kilometers. And I think there's some pretty concrete reasons to do that. There's pretty good evidence that if you have a square that's 100 by 100 kilometers and it's inside of a species range, that species will actually occur inside of that square. When you have a smaller square, there's a pretty good chance the species is not showing up in that local community, even if they are, inside of the species range. So I think that's a good kind of scale to think about a regional pool as occurring. Local communities are necessarily much, much smaller than that. Depends on your organisms, could be 0.5 meter by 0.5 meter, 100 meters by 100 meters. I'm going to work with the BCI data, so my local communities will oftentimes be 100 meters by 100 meters. Okay, so I asked the question, just literally pulling marbles out of a jar, how close can we get to reproducing patterns? Up on the top left, there's a species area relationship. So area across the x-axis, number of species on the y-axis. In each of these graphs, the blue is the predicted, or what comes out of a sampling model, and the gray or black is what's actually observed with BCI data. And you get a species area relationship out of this, but you don't get a very good one. And in particular, the problem is that every species, so in this case, we have 50 hectares, 50 100 meter by 100 meter plots is my regional community. And every species is in every hectare very, very quickly, or not hectare, but it looks like you get up to five hectare plots and every species is showing up. So the species are spread out too thinly or too evenly across space. The actual species richness in the average hectare at BCI is about 90, but the random sampling method gets 200, almost 200. So it's really the same issue. They're spread across, and you don't get species differences. So the occupancies are equal. So I should mention this is the extreme null model where there's no every species is equally even. Every species has equal abundance. So I'm just kind of maybe belaboring an obvious point that you need to know what's a rare species and a common species. You need to have that, or you get things completely wrong, as this graph is showing. Oddly enough, that last one is Morosita horn beta diversity, and those end up actually pretty close. But as we'll see, that's a case of, I think, 2 errors making a right. You don't normally get things that close in beta diversity. So, okay, so we can't literally have a marble, we can't have a regional pool that is every species is equally abundant and I'm randomly sampling from it. So that probably should have been obvious. Let me take it to the next step. and say, we know that there's, one of the core patterns in community ecology is that many species are rare and a few species are common. And these are order or magnitude kinds of differences, right? This is the species abundance distribution. It's log normal. You see one on the left for Barrow, Colorado Island, one on the right for the US forest inventory. And I should point out, this is something you don't see that often. These are the regional species abundance distributions, not local community, but they look just like local community. Put them on a log scale, they're kind of normalish. There's some debate about the left tail and if you have an excess of rare species, but they're kind of log normalish. So we know there's a lot of rare species and a few common species, and that's true at the regional scale too. So what if we go ahead and wire that in? And I'll notice you don't have to have an actual empirical species abundance distribution. You could just use a you could assume a log normal distribution or something like that and have some scale of the total number of species in a community. That's all you need. I do actually here use the regional species abundance distribution because BCI does have this weird sort of pattern that doesn't fit any standard shape particularly well. And now we do a whole lot better. So that species area relationship is close. It's systematically wrong, over predicting and under predicting, but it's close. Local richness in a 1 hectare plot is much better. We're predicting 100 and we actually have 90. That bottom left panel is now the occupancy abundance. It's the predicted occupancy based on abundance. And you would hope it's all on the 1-to-1 line. We're at least scattered around the 1-to-1 line. Beta diversity is much too low. We have way too much similarity between hectares. So too much alpha, not enough beta diversity. So this goes back to the fact what we saw originally, that and that also explains this systematic excess of species at small scales, because we don't have enough beta diversity. We pick up more beta diversity. Sorry, if we had more beta diversity, we'd pick up more species more slowly. So all of these have the same problem: too much alpha, not enough beta. And so again, it's not as bad as when we assumed every species was equally abundant, but we're still getting species spread out too much in space. Species are too likely to show up with just a few in each of the boxes that we're looking at, each of the local communities. So that's overestimating alpha local richness, and it's underestimating beta diversity. So we need another. I mean, that's not terrible, predicting 90 versus 100 plus or minus 10%. That for ecology, maybe that's not terrible. Maybe that's good enough. But if we want to do better, we do need to add another assumption. And I think before I do that, so these have been Monte Carlo. These have been literally like resampling from BCI data. I'm now going to make a transition, since this is the theory talk. I'm going to make a transition to an analytical framework, and then I'm going to talk about that missing assumption. So the key feature that you need is what I'm calling a sampling function. And so it's the probability that the local community has small n number of individuals of species I, and that's conditioned on the number of individuals of that species in the meta community, large N, the area of my small community, the area of my regional community. That's really just to get a proportion of the sample, and some unknown other set of parameters. And that's really the question, is how many parameters do we need to add to the sampling function? And this is all reviewed in that 2011 paper, but I'll note that it's, most of these formulas have been published previously in a number of other places. And again, I think John Hart and, got very, very similar in spirit to this, as did, some of the later work on neutral theory, like that paper by Paul Etienne and David Alonso, very much had a sampling function kind of concept as their implementation of neutral theory. So this idea has been around in theory. Like I say, none of these formulas are original to me, but I'm the only one who's crazy enough to kind of go whole hog and actually see if we can really predict all of community ecology and pull this all together. That's really just my contribution. Okay, so here's the species area relationship. It's the number of species as a function of area. And the number of species is, this may take a minute to think about, it's really the sum of the occupancy of each species, but the occupancy of each species is really just the sampling function. So we have to sum over all possible abundances and all possible species, but we basically get a formula for species richness as a function of area, which of course can predict local richness at any scale. Here's occupancy, same thing. Occupancy is 1 minus the probability of having no individuals in the sample, right? Remember, this first slot is the number of individuals. The local species abundance distribution, which I'm denoting here by mu, so this is the proportion of species that have an abundance of J, is really just a convolution of the regional species abundance distribution with a sampling function. You can get various metrics of beta diversity. The Sorensen is the easiest to pull out, but again, it's really sort of a convolution of a squaring of the regional species abundance distribution with a sampling function. So the key point is all these patterns that I'm talking about are linked together by this core idea of a sampling function. And again, lots of people have said that. But the sampling function becomes central. And then the question is, we know we need these parameters. We need to know what fraction the sample is. We need to know, as little n gets close to big N, we're increasingly in a sampling without replacement scenario. As little n is small compared to big N, we're more in a sampling with replacement scenario. And how many other parameters do we need? So again, this is really analogous, but this is an analytical calculation. So this is regional variation in species abundance. But the last slide I showed you was a Monte Carlo simulation. These are analytical results that I'm presenting here, but as you might hope, the analytical results are pretty close to the Monte Carlo simulation. We do fix this area, the species area relationship, but we're still systematically over predicting local richness, whether we look in a species area relationship or we look down here at the histogram. And the occupancy abundance relationship, we're systematically over predicting occupancy. We're predicting the species is in more plots than it actually is based on its abundance. And this plot is just the difference between the two species area relationship. So this is actually very close. I'll just show you quickly. It looks very, other than fixing this part over here, it looks very similar to what we got, very, very close to the Monte Carlo. And so, the analytical approach and the Monte Carlo approach tie out, that's good. But now my goal, now that I'm in an analytical framework, is to see what's missing to make these things, again, pretty good. You could stop here. Wouldn't be crazy as an ecologist to stop here, but I want to see if we can go further. And so the thing that's missing is we know that individuals within a species are not spatially random. Individuals within a species are almost always clumped. They're spatially clumped. They're not over dispersed and spread out evenly, which was the big hypothesis back in the 70s due to competition, but they actually tend to be more close to each other individuals of the same species than they would in a spatially random chance. So they're not spatially random, they're clumped. And you can see this in lots of ways. This is from a paper by Rick Condit at BCI. This is using the paracorrelation function, where they actually use the omega function, which was just a constant multiplication of the paracorrelation function. Anywhere it's above 1 represents clumping. Anywhere it's 1 represents spatially random, and the x-axis is spatial scale. Here's another paracorrelation function that I calculated from the forest inventory, US forest inventory. This is a visual representation. So this is one species, red maple. So even across a whole species range, right, there's clumping. There's an area of concentration where the abundance is quite high and a pretty large area where the abundance is quite low. This is a plot of BCI. Number of people who looked at this. I think John Hart was one of the people who first called my attention to it. But if you assume a Poisson distribution, you tend to get this peaking around the mean expectation, which would be the number of individuals divided by the number of plots. But you actually get over dispersion. You either get a lot of zeros or you get really high numbers. You don't get 5 individuals in every plot. You get a bunch of zeros and a bunch of 30s and 40s. So this is another expression of that clumping. So clearly Poisson is a representation of spatial randomness. Clearly Poisson is missing this clumping feature. So so we have a sampling function. We allow ourselves to have more parameters. It would be nice if we could throw in a parameter to represent clumping. And this I'm really borrowing very heavily. There was a nice paper. I don't think it's got anywhere near the attention it deserved by Tommaso Zilio and Fengling He in 2010 in Ecology. And they came up with what they call the finite negative binomial distribution. It's been pretty common to use the negative binomial distribution as an extension of the Poisson. And indeed, as the K or clumping parameter in the negative binomial goes to infinity, it collapses to the Poisson. The problem is this is an infinite sample. It's just basically a sampling with replacement, or a sampling at an infinitesimal level. And when you're dealing with regional pools, that doesn't quite work. So you need to move over to the world where you have finite samples. Spatial randomness is represented by the binomial distribution. And the finite negative binomial distribution is, if you want to think of it conceptually, an intersection between the negative binomial distribution and the binomial distribution. So it converges to the binomial as the clumping parameter goes to infinity. As K gets closer to 0, things are more and more strongly clumped. This is just some plots. So here's A, the proportion being sampled of 0.1, 0.3, and 0.8. And the black dashed line is the binomial distribution, unclumped spatially random approximation. And across the x-axis, we have K going from 0.1, and you can see it's really quite extreme here, right? The binomial has exactly, 30% of the individuals showing up in each plot, whereas the finite negative binomial has almost all zeros or all in one plot. And as we relax K, we start to get more and more central tendency in the finite negative binomial, and eventually we start to converge on the binomial or spatially random as K gets very large. So here's just a couple examples from BCI. It's a 50 by 100, sorry, it's a kilometer by a half kilometer, or a 5 by 10 hectare plot. So here's a species with a very large K. I cap my K fitting algorithm at 10. You'll see why in a minute. But this is basically spatially random. Here's another one. These are all tree species, spatially random. Here's a couple examples with K equals 1, which is pretty clumped, but not as clumped as you can get. And you can see there clearly is visually much more clumping going on in these species than there are in these species. So you can, there's a maximum, like it's all in the Zilio and Hay paper, there's a maximum likelihood approach to estimating K. So you can estimate K if you have the data. And so I estimated K for all 225 species in the BCI plot. And I estimated at 3 scales, 1 hectare, 5 hectares, and 25 hectares. And here's the histogram of Ks. And what you see is you get this kind of bimodal distribution where a lot of species are highly clumped and a lot of species are fairly reasonably spatially random. Again, I capped this at 10. There's a bit of a shifting with spatial scale. The 25 hectare has more spatially random species. This is supposed to be violin plots, but there's such a strong spread. It's such a skewed and bimodal distribution. It's really a hard distribution to work with or plot. The black line goes to the mean. The dashed line goes to the medians of these values at 1, 5, and 25 hectares. Here's 225 species all plotted at once. And the black line is the average fit across, and that's not statistically significant from 0. And you can see if you fit a power law, the exponent's 0.01. So there's been a lot of talk about the scale dependence of K. It's actually not that strong. What I found is much more strongly is a scale dependence on the abundance of the species. Not necessarily scale dependence, but K depends a lot on the abundance of the species. And there's, again, you get these Ks that are racing off to infinity, and I stopped them at 10. And it's a little hard to know how much that's real and how much that's a small sample estimation problem. But if you ignore those, there's really a very strong slope. If you include those, there's a modest slope, an exponent of 0.14. So this is a fit looking at both N and K. And by the way, the fit is terrible. The R squared is like 0.10. So K is highly variable, but just to get a sense of what's happening with K. And you can see here, abundance has a much bigger effect than area, but area and abundance affect the K parameter of the finite negative binomial distribution. All right, so we know about K. And the goal was to try and make our community estimation of community properties better. So here's an example where we let K, I took K at 3 scales, 1, 5, and 25 hectares. And I took K from each species. So I'm basically, it's a very parameter rich, very parameter hungry model. It's taking K from each species, which arguably is cheating. It's right, sneaking a lot of species spatial distributions into the model. Species area relationship works pretty well. It breaks a little bit at large scales, which doesn't surprise me because I wasn't estimating K so much as those large scales, but the errors in the species area relationship are down to about 7 to 10 species. Even so, we're within about 1.2 species at predicting local diversity. And this is a nice graph. Erin Conlisk has a beautiful paper where she looked specifically at this with the occupancy abundance relationship and showed exactly what I've shown, which is you tend to over predict occupancy until you deal with a spatial clumping. And then when you deal with a spatial clumping, occupancy and abundance basically become the same thing. Once you control for abundance and clumping, those two things become interchangeable. Or another way is if you know clumping and abundance, you can predict occupancy with a high degree of accuracy. And so it works pretty well. Really, the only thing to complain about is maybe a little systematic deviation here, but maybe that's because I use discrete scales for K. So it works really well, but this is really parameter rich. I just wanted to explore, can we go somewhere between binomial and throwing in, what was it, 450 K parameters, which is, excessively parameter rich. So here's an example where I just took the average K across all scales and all species. So a single K number. I forget what it was, but it was somewhere around 2 was the K that came in. Actually, this does pretty, that depends. Got species area relationship pretty well. It's a little worse, but it does pretty well. Does noticeably worse, in particular, right around the 1 to 5 kilometer, hectare area. We're back up to being 8 species apart. This relationship is tighter than before, but it's clearly got some species drifting. Some other variants that we could try, letting K vary across species, but not across scales. So averaging the K across scales for each species, so 225 Ks. It's a little better, but not worth adding in 224 parameters, in my opinion. Another choice is to let K vary across scale, but not species. So here I threw in my 1, 5, 25 K, so I only had 3 K parameters. And that looks pretty darn good. Species area relationships off by just a couple of species. Species richness is actually even slightly better. It's down to 1 species, and the occupancy abundance relationship is quite tight again. So that's, and last but not least, very similar in spirit is actually taking from that regressions that I was doing early on of K versus scale. So letting K vary with scale, really technically this has 2 parameters, right? The slope and intercept, or the coefficient and exponent in a power law relationship between K and scale. And here's our species area relationship. Here's our local diversity prediction, 1 hectare diversity. And here's our occupancy abundance relationship, quite tight. So this model is predicting local richness, species area relationships, scale dependence of richness, occupancies. I didn't look at species abundance distributions here, but they do come out fairly well too. And this has 2 parameters to address K. This has, and this has the distribution of regional abundances, which I chose again because there's not a nice functional form to fit, to just borrow the empirical data, but I could have thrown in a log normal or something. And I have played around with that. That works pretty well too. At that point, you're down to 4 parameters, right? The shape of the regional species abundance distribution. Well, actually a density, which lets you go back and forth between area and number of individuals, and 2 parameters for K. So this is 5 parameters to describe local communities as sampling from a jar, but it's a biased sampling. If I pick a green marble, I'm much more likely that the next marble I pick is green, right? So it is earned sampling of marbles, but it's a biased, you can call it biased or clustered clump sampling. If I pick, once I pick a green, it's much more likely that the next green, the next marble is also going to be green. That's the statement of clumping. Okay, so I want to make a point that this theory works extremely. You may know the species area relationship is triphasic. This is a triphasic species area relationship for birds. This is actually one of the original triphasics from MacArthur's paper. No, I'm sorry, Preston's paper back in the 60s. And you'll notice these red dots. It's a triphasic, right? Increasing, flat, increasing. And I would note that this theory really works very well up to about that scale break that I mentioned of about 100 by 100 kilometers, which would be right here at 10 to the fourth. So it's explaining this part, the increasing, decelerating into a flat part of the region. Doesn't explain this part. I'm not going to spend much time on it. In fact, one slide, but I just want to point out that there are papers that do this that have a very similar spirit, in which I'm throwing down circles on a square, and these circles represent species ranges, and I'm putting Gaussian or normal or bell curve shaped distributions of abundance. Not surprisingly, Whitaker was one of the first people to look at this. But if you do that, you can actually get, so it's again very similar in the sense that it has variation in abundance, or in this case, range size, rare versus common species. And it also has variation in abundance in the sense of the heights, maximum heights of those peaks. And it has clumping. In this case, the clumping is defined by the normal distribution and the fact that you have pretty large tails where species are not very abundant and fairly small areas of peak where they are highly abundant. So it's really got the same assumptions. And I'll just point out, it does do the species area relationship at these larger scales from 100 kilometers up to continents. Yeah, so I'm not going to spend a lot of time on that, but check out those papers if you're interested in that. Well, I said one slide, but here's 3 slides. So here's the idea, right? Random ranges, and then you sample an area. And here is the species area relationship predicted for that larger. It does really bad at the small scales. So we take the marble model at small scales up to about 100 by 100 kilometers. We take the Gaussian bell curves for large scales over 100 by 100, and we have quite a bit of explanatory power. I'm not going to spend a lot of time on this. This is a paper with Jeff Nicola. But we can extend the same idea, not surprisingly, when I was doing beta diversity, but decay of similarity with distance. So this is Sorensen's similarity with distance. And you take this core idea that each species is independent of every other species, and you develop the idea of decay of similarity with distance within a species, which is a statement about the probability that if a species is found here, what's the probability that it's in a box with a distance of d away, and you end up producing decay of similarity curves quite well too. So really, this paradigm of independence between species, clustering of individuals within a species, variation in abundance across species, really carries you very far in the patterns in macroecology. So I'll summarize and stop. So inputs, the shape and scale of the regional species abundance distribution, some knowledge, and I was playing with how much knowledge about clumping of individuals within a species, and some basic knowledge about the size of a local community and the walking back between area and number of individuals or density. Those are the inputs. And we can predict alpha diversity, beta diversity, scale dependence of alpha diversity or species area relationships, occupancy abundancy relationships, decay of similarity with distance. And I haven't shown you this, but local species abundance distributions. That's a pretty big hit list for the patterns of macroecology and community ecologists want to understand. And they all can be produced by marble sampling. Implications of this, I'll be curious to have this conversation with you all. That's what I'm looking forward to. But clearly, you know, there's needs to be more testing of this. This was BCI, right? It's one group of organisms. I've done some work with the breeding bird survey and the forest inventory. I think it largely generalizes to that, but clearly more work is not needed. It really highlights this K parameter. Understand, or, you know, even if you don't like the finite negative binomial, just understanding the clumping, the distribution of individuals within a species, how that varies with species, how that varies with traits, how that varies with abundance, how that varies with scale, seems like a really key understanding that we are mostly missing. Is there a way to bring species back in? I'm not going to go there today because I wanted to stick to the spirit of 30 minutes, but I think traits may be part of the answer. And the other big conclusion is this, to me, is just pointing at a giant arrow at we need to spend a lot more time looking at the processes at the regional pool and less time at the processes at the local community level. We really need to understand if the local community is to a first approximation, a random sample, even if it's a clustered random sample of the regional pool, we should spend a lot more time understanding what's structuring the regional pool. And there's clearly evolutionary dynamics and large spatial dynamics that are happening there. So I'll stop there and happy to take questions. I guess I'll stop sharing so we can see each other while we're talking.
Thank you very much. Thanks. So in order for asking questions, if you click the reactions button down the bottom, there should be a button for anybody to raise their hand. Well, auto clap first, but if you raise hands, then it will be able to call on people to unmute and ask any questions. Or you can ask in the chat as well. So there's someone from Sergio Velina. Do you want to unmute and ask a question?
Yes, can you hear me fine?
I can.
All right, thank you. A very nice presentation. I want to have your point of view regarding, as far as I understand, your approach was to have given an amount of species in the community and the abundance of them, retrieve or recover alpha diversity and beta diversity and all properties like SAT, etc. My question is the other way around. If you have, let's say, a map of alpha diversity and you know the beta diversity as well in space, is there any way theoretically to recover the total amount of species in the region or the gamma diversity? Do you know if this is possible?
Yeah, so that's an interesting question. It's clearly a related question. There's some people, I think of like Bill Coonan, who has worked on that problem. So kind of an upscaling approach. But yeah, so a lot of the upscaling, I think, started with trying to work with just abundance. And I think, so I think what clearly is highlighted here, and you said it yourself too, is that you have to know something about the beta diversity. And the beta diversity really is a way of capturing this clumping, right? Those two things, they're different ways of describing spatial distributions or patterns across space. It's not enough to just know abundance and splat the marbles down in space randomly. You really have to know something about how those marbles tend to segregate or not segregate to get the upscaling. And so, yes, there are people who are working on the opposite problem, which would be, if I was doing the downscaling problem, which would be the upscaling problem. If I have, and that clearly has some nice conservation applications. If I know a lot about my local community and I want to predict my regional community, how much can I do it? And it does go, the equations are different, of course, but they're mostly power law kind of scalings, but goes through the same basic principles of the math, right? That you need to know about abundance and you need to know about spatial structure of individuals within a species or beta diversity.
Thank you very much.
Jeremy, do you want to go ahead?
Hi, Brian. Enjoyed the talk. I figured that you would be disappointed in me if I didn't ask the question I'm about to ask, which you probably saw it coming from 10 miles off because we had this argument on the blog years ago. As a community ecologist, what I want to push back on this earned sampling idea, because at some level, right, it just has to be a fiction, right? At some level, your regional pool, whatever its properties are and whatever scale you define it at, that regional pool that you're seeing at any moment in time or at any location in space is ultimately just the outcome of organisms giving birth, individual organisms giving birth, dying, and moving around, right? It's ultimately endogenous. Right? It's not some exogenous thing, right? It's the emergent outcome of lots of individual organisms that have moved around and given birth and died over a long span of time over the planet, right? And so I guess the question is, how hard would it be to, or what do you have to do? What are the properties? What assumptions do you have to make about individual organisms giving birth, dying, and moving around, and the rates at which they do those things, and the way those rates vary among species and over space? What assumptions do you have to make to then get a world in which your regional sampling model, your EARN model works? How tightly are those processes of individuals giving birth, dying, and moving around constrained by the fact that, okay, this regional model works and it has these properties, right? Is it just like, can we assume just about any old thing about births and deaths and movement, or are there actually pretty tight constraints on what we can assume? What do you have to assume to get a world in which the emergent property of regional pools is such that you can pretend that you're sampling from them and get it to work?
Yeah, so, I mean, first off, stipulated tautologically, the regional pool is on some level the sum of millions of births and deaths locally, right? I mean, that's just tautological. But I think the question is that a useful fact or not, right? And you know, opinions are going to differ about how successful we have been from scaling up individual births and deaths up to a regional scale, or you know, or even to a local community. I think is a fair question, how much that approach has added to our knowledge about local communities. So I think it's helpful to go back, right? The two things I had to bake in and why it wasn't just pure marbles was variation and abundance, right? And clustering. So the clustering, I think, is pretty easy to tie to two processes, one of which is local, right? Dispersal limitation. Things tend to be dispersed close to where they came from. So dispersal limitation clearly is part of the clustering story. I think the other part of the clustering story, though, is fit to environment, right? If you have a micro community, micro environmental variation, some areas that, you know, a species is better adapted and worse adapted, and that's, yeah, you can run it through the population paradigm, and fitness varies on environment, but again, how far have we gotten with that program at explaining things at a very large scale? The variation in abundance, I think, is, I know there you can run Locke-Volterra equations with certain constraints on, you know, the coefficients and things, and end up producing communities that have log normal distributions of abundance. But to me, it's just a whole lot more parsimonious to just say central limit theorem, log normal distribution. So, you know, tautologically, yes, it scales up. On a practical level, I'm not sure how much the fact that we have 1 million births and deaths going on tells us about a regional process. I think it's, you know, so far looking at climate limitations on regional processes has told us a whole lot more than looking at local birth death processes informing regional distributions. So, you know, but ultimately that's what makes science fun, is everybody's got a different approach, and in the end, the approaches that work hopefully are successful and move forward. So I guess we'll see over time how things pan out.
Yeah.
And I'll just, I more or less buy that. I more or less buy that answer. Okay, there's a combination of spatial autocorrelation in the environment and dispersal limitation, plus it's really hard to write down any process-based model of births, deaths, and movement that doesn't give you like a bunch of rare things and a few common ones. So, yeah.
Yeah. I mean, I'll notice there was a chat in the, Abdel had a question about clumping and local approach. I think we kind of addressed that too, so I'll just note that.
In which case, next up would be Martin Wilkes. Do you want to unmute and ask?
Thank you, Brian, for a fascinating talk. I wanted to ask about going back to the processes behind that shape communities. There's been some interest in using these kinds of approaches to understand the relative importance of niche-based dispersal or generalized spatial processes. I guess it means bringing back species identities rather than the marble sampling. So, you know, when you take processes out or you put processes in, how much better are you at predicting community structure and species identities? What do you think are the prospects for sort of having that level of insight from these models? Yeah,
so, you know, that's the big thing that's obviously the elephant in the room that's missing is species. You know, once you know if they're rare or common, you don't need to know anything else about a species to put this together. And, you know, I think that was the same reason people had reactions to neutral theory or maxent. They kind of take the species niches out. And you know, I go back to the kind of pragmatic question that I had with Jeremy. It depends on what you're trying to do. There are places where it appears to be really useful to just ignore niches and species identities. And there are places where it really doesn't work. Obviously for conservation, it really doesn't work to just ignore species niches and species specifics. On the other hand, for some, you know, patterns, the kinds of macroecological patterns I'm talking about, species identity and niches seem to come out in the wash a little bit. On the other hand, I do think that, you know, I kind of hinted at it and I don't have time to get into it today. I do think traits are a way that we could start to bring species properties back into this. I always get worried about bringing in species one by one by one, name by name by name. You know, Acer rubrum was the red maple I had up there. You know, if we try and bring in Acer rubrum and everything we know about Acer rubrum, again, from a conservation perspective, or, you know, if I'm a sugar maple, you know, if I'm growing syrup, that's an important thing. But if I'm really trying to understand how systems work, that doesn't lead to generality. So I always have a bias towards generality. And I do think there's ways to tie traits. I think it's early days in traits, so it's an open question, but I think there's ways to start to tie traits to some of these properties. I mentioned very briefly, I'd love to know what the links between traits and abundance have not worked out very well, but I'd love to know the links between traits and the K parameter, for example. And yeah, so I guess, you know, other than saying, yeah, it's important to study individual species, whether they can bring them into here, I think traits have some potential, but I also think to some degree, you're just going to leave species behind when you look at these kinds of questions and scales of dozens of species and hundreds of kilometers.
Adam, let's go.
Hi there, can you hear me?
I can.
I really liked this. It's a very clean framework. So I feel like this was this was very helpful from an organizational perspective for me. I just want to make sure that I haven't misunderstood something. My sense is that this is very much a descriptive framework, right? As in, I can't really think of a way that you would use this to, for example, forecast how the patterns might look different in 20 years, or after it gets 10 degrees warmer, or after you lose 5% of the species in the system. Is that right, or am I missing something?
So, no, I mean, that's a great question. And I've thought a lot about that myself, because I'm, you know, I like the forecasting paradigm. Where forecasting comes in is that link between climate and the regional parameters, species richness, density of individuals, clumping. And that's clearly where global change is impacting things, right? In fact, it's probably a lot easier to get your head around global change and how that's changing total abundance, how that's changing species richness, how that's changing clumping in landscape, you know, heterogenization or homogenization. So I haven't done a lot, but once you have those parameters, you can actually predict local diversity and things like that. So to the extent you want to predict, again, what's the fate of the red maple or the sugar maple, no, it's not at all predictive. But to the extent you're trying to make the big kind of macro management kinds of predictions about how is local richness changing, how is beta diversity changing, I would argue that I'm actually opening up the handles that are more accessible to global change than a bunch of individual level models, right? So again, species richness, total abundance, density of individuals across the landscape, clumping, these types of things are things that it's really easy to start to imagine how. Now I regret not putting it. I did have one slide that just kind of shows as you turn one of those knobs up and down, how community properties change. So, I mean, if you want to predict individual species, definitely not. But if you're looking at global change impacts on community structure, I think actually this framework has a real potential to open up some predictive capacity that doesn't necessarily exist through other approaches.
Cool. Thank you very much.
Thanks. Vivek, I think you were next.
Yeah. Hi. Thank you very much for this inspiring presentation. My interest is to understand decision making at local scales, especially in agro-ecosystems. How we could use, I come from biodiversity ecosystem function research data. How much time series data would it be needed to come up with some kind of management decision making about species abundance or even available in particular agroecosystems? For example, in finance, in some papers are telling that for forecasting the stock performance of in the financial system, for 50 numbered portfolio, we'll be needing 500 years of data of stocks. Like that, how much time series data would we be needing in ecological systems, even at macroecological scale or local scale? Are there any predictions like that about length of time? Thank you very much.
Yeah, so I mean, this builds a little bit on my answer to the last question, but this is pretty much a static prediction at a point in time. Once you go from the regional community down to local communities, it's so the change component comes in at the change at the regional scale. So really what you would want to be doing is understanding changes in these parameters, richness, density, evenness of the species abundance distribution, clumping, these kinds of things at the regional scale, and how those are changing based on management practices, global change dynamics, and things like that. So the answer is going to vary, but in my experience, you can get quite a bit of information about a number of those parameters with 20, 30-year kind of time series. So it doesn't put it into the 500 years out of the realm of possibility. Probably the bigger challenge is you need those data at a regional scale, which is not the scale we necessarily measure at that often, and not necessarily an easier scale to measure. So I think perhaps the space dimension is the bigger challenge than the time dimension on this. But the time dimension, I think those correlations or links often play out over 20 or 30 years in a pretty visible way.
Yeah, thank you very much. Thank you.
We're just coming up to the hour, so I just wanted to check, Brian, are you happy to carry on, or would you rather round up? I don't want to take more time.
I'm happy to keep going.
Okay. So there was a question in the chat from Aaron Westmoreland. I don't know if you're able to see it, but it's basically asking about processes that might determine the distribution of K.
Yeah, I've thought about it at an ecological level. I haven't thought it too much at an evolutionary level, but again, when I think of K, I think of two things: dispersal limitation and fit to environment, right? And so, so there's evolutionary processes around dispersal limitation, just as there's ecological processes. And the other evolutionary processes I would see, it really is getting to the specialist generalist part of things. That gets to how much you require adaptation to a very specific micro niche at a micro environment scale. And it also, of course, gets to this big question, or at least we think. I've never seen a really convincing study that convinces me, but we think it's related to when a species is rare and common at a macro scale too. So specialist generalist trade-offs and dispersal limitation trade-offs are probably the two that I would think of most immediately about evolution.
Yeah, thanks. I think we're back to Jeremy again then.
Yeah, my second question kind of follows up on something we've just been talking about a bit here in response to Vivek's question and the last question. Because of course there is a bit of kind of process-based work on this, on the evolutionary side, right? People have played around a bit with like, well, what if you link some kind of like neutral model? You've got some sort of neutral model for the demographics, and you also build some evolutionary model with speciation, and extinction in it. What do you have to assume about the evolution to get it to spit out sort of realistic phylogenetic trees and get realistic biogeography out at the end on the ecological side? And my impression of that literature, though it's been a while, I look at that literature, is that the few attempts that have made have actually not been that successful, that you can't just sort of assume any old thing about speciation and extinction on the evolutionary side and get reasonable phylogenetic trees and also get a reasonable biogeography out. So I guess the question is, do you think there's potential there to incorporate more? Because a lot of what you're trying to do, right, is like, we have, we're going to look at kind of a bunch of, response variables at once, right, and push and see how many of those we can predict. Do you think we should just keep going like that? Like, let's bring in some evolutionary response variables too, to do with things like shapes of phylogenetic trees and, mapping the distributions of species on the landscape in relation to their evolutionary history. And maybe, if you have enough response variables together, that gives you enough constraints to really say, like, all right, here's what the underlying features of the environment and the demographics and the evolutionary stuff too has to be able to then generate all those dependent variables.
So absolutely agree. The regional pool is a lot about evolutionary processes. It's also, and how they interact with climate. My goal is not to build the one model to rule the world, but to build models that show strong couplings and weak couplings. So you can take those strong couplings and use them to leverage yourself up to a different scale, and then, find the scales where we have good explanatory power. So for me, that's what this program is all about. Is I think we have more explanatory power at the regional scale than we do at the local community scale. And whether you're trying to scale up, as we had one question, you're trying to scale down, there's a strong coupling between the local and the regional. And so for me, that just means we can take our work up to the processes at the regional scale. And we have spent a lot less time on that. You're right. There's, neutral or random speciation models out of neutral theory that have looked at regional processes. And there's some other work, and, the climate species richness relationship's been pretty heavily studied. But my intuition is that we're going to have a lot more biology and a lot more success understanding these emergent properties at the regional scale than we have at the local scale, because the local scale and regional scale are so tightly tied together. And, the community scale, let's see if I can defend this statement. I was going to say the community, John Lawton made this statement about community ecology is hard because it's an intermediate numbers problem. And I tend to match that intuition. So when you're doing populations and single species, you get something that's tractable. And when you get the regional scale where you're talking about millions of individuals and statistical laws dominate, when exogenous forces aren't dominating, seems tractable. The community scale seems hard. So for me, this is like an escape from the community level to the regional level, because I think we're going to be able to do a lot more about the process at the regional level. But I would not try and then hook that into a giant model that, has a speciation parameter that trickles down to local communities. That, although, I guess that's what neutral theory tried to do. But for me, the whole point of this is to say, okay, these two things are strongly coupled. There's nothing that's clearly strongly coupled to communities, but there are things clearly strongly coupled to the regional processes. So let's study those things that are strongly coupled to the regional processes. And yes, phylogenies are one of them. And I read the literature the same way you do, that neutral speciation is not necessarily a great answer.
Thank you. Yakwan, thank you for waiting. Did you ask your question?
Yeah, can you hear me?
I can.
Yeah, thanks a lot for your presentation. And my question is, so can this framework apply in the mountain regions?
I'm sorry, a framework apply to mountain regions?
Yeah.
Yeah. So that's a good question. When I say 100 kilometers by 100 kilometers, I'm definitely not thinking mountains. This is mostly taking environment as constant across the regional pool. So I think my short answer is no, it probably doesn't work great along steep environmental gradients like a mountain region. But that would be a really interesting area of work to see if you could extend it and, put a linear environmental variable across these. My communities are just a random sample from the regional pool. So that's sort of implicitly assuming every plot that I'm sampling is environmentally constant. But it would be a really interesting, I mean, the one exception to that is if density is changing across, right, the number of individuals per unit area. That would be pretty easy to incorporate. Anything beyond that, I think would be a really interesting, but definitely a new direction to go from what I've been doing.
Thanks so much. That seems to be the end of any questions that have in the list. If anyone wants to ask anything final to Brian, now's the time to shout. Looks like not. So I'll say, yeah, thank you so much again, Brian. It's a really, really interesting talk. I hope the discussion's been pretty good and lively, actually. Lots of questions coming in from all sorts of angles. So I guess that just leaves me to say that do join us next week in 2 weeks' time. We've got Axel Rosberg is going to be talking about the evolution of prudent predation, if I remember right. Jump in if that's changed. But yes, thank you very much. Thank you, Brian, and hopefully see lots of people again soon. Thanks a lot. Bye.
Thank you.